The National Electrical Code, or NEC, mandates the use of a grounding conductor for all service entrance conductors. Omitting a grounding conductor in electrical service changes is a violation of the NEC and creates significant safety hazards. The purpose of a grounding conductor, also known as an equipment grounding conductor or AGC, is to provide a low impedance path for fault currents to return to the source. This low impedance path facilitates the rapid operation of overcurrent protective devices, such as circuit breakers or fuses, in the event of a ground fault. Without a grounding conductor, fault currents may not have a clear path back to the source, which can result in elevated voltage levels on metal parts of electrical equipment, creating a shock hazard. Furthermore, a grounding conductor plays a role in protecting against lightning strikes. It provides a path for lightning current to flow to ground, minimizing the risk of damage to electrical equipment and reducing the potential for fire. The NEC specifies the requirements for grounding and bonding in Article 250. Article 250.4. A5 addresses grounding of electrical equipment. It states that normally non-current carrying metal parts of equipment shall be connected to a grounding electrode conductor and grounded in accordance with specific sections of the NEC. This requirement ensures that metal enclosures, raceways, and other conductive parts of electrical equipment are at ground potential, reducing the risk of electric shock. The size of the grounding conductor is determined by the size of the service entrance conductors. Table 250.102. C1 provides guidance on the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. For example, if you have two 100 ampere service entrance conductors, you need to refer to Table 250.102. C1 to determine the appropriate size of the grounding electrode conductor. It is important to select the correct size grounding conductor to ensure that it can effectively carry fault currents. Installing service changes without a grounding conductor has several consequences. Firstly, it significantly increases the risk of electrical shock and fire. Without a grounding conductor, fault currents can flow through unintended paths such as metal conduits or water pipes, creating a shock hazard for anyone who comes into contact with these energized surfaces. Secondly, it can cause damage to electrical equipment. Fault currents can overheat and damage electrical components, leading to premature failure and costly repairs. Thirdly, it may void electrical warranties. Many manufacturers require that their products be installed in accordance with the NEC in order to maintain warranty coverage. Installing equipment without a grounding conductor may void the warranty, leaving you responsible for any repair costs. Fourthly, it will result in failure of electrical inspections. Electrical inspectors are responsible for ensuring that electrical installations comply with the NEC. If an installation is found to be lacking a grounding conductor, it will fail inspection and require correction. To correct an installation that is missing a grounding conductor, you must run a new grounding conductor from the load side of the meter to the panel. The grounding conductor should be connected to a grounding electrode, such as a ground rod or a metal water pipe that is in direct contact with the earth for at least 10 feet. The connection to the grounding electrode must be made using approved methods, such as grounding clamps or exothermic welding. In addition to running a grounding conductor, it is also important to ensure that all metal enclosures and raceways are properly bonded together. Bonding creates a low impedance path for fault currents to flow, helping to clear faults quickly and safely. Bonding can be accomplished by using bonding jumpers, bonding lock nuts, or other approved bonding methods. When performing electrical work, it is essential to follow all applicable safety precautions. Always to energize circuits before working on them and use appropriate personal protective equipment, such as insulated gloves and safety glasses. If you are not comfortable performing electrical work yourself, it is best to hire a qualified electrician. Electrical work can be dangerous, and it is important to ensure that it is done safely and correctly. The NEC is a comprehensive set of standards that governs the safe installation of electrical wiring and equipment. It is updated every 3 years to reflect changes in technology and best practices. Staying up to date with the latest edition of the NEC is essential for anyone who works with electricity. In summary, A grounding conductor is a critical component of electrical service changes. It provides a path for fault currents to flow to ground, protecting people and property from electrical shock and fire. The NEC requires that a grounding conductor be installed for all service entrance conductors and that it be sized according to the size of the service entrance conductors. If you have installed service changes without a grounding conductor, you should correct the issue as soon as possible. This can be done by running a new grounding conductor from the load side of the meter to the panel and ensuring that all metal enclosures and raceways are properly bonded together. Always follow all applicable safety precautions when performing electrical work, and if you are not comfortable performing the work yourself, hire a qualified electrician. Remember that electrical codes and regulations can vary depending on your location. Always consult with your local authorities or a qualified electrician to ensure that your electrical work complies with all applicable requirements. Understanding the importance of grounding and bonding is essential for ensuring the safety of electrical systems. By following the NEC and implementing proper grounding and bonding techniques, you can help to protect people and property from the hazards of electricity. The absence of a grounding conductor presents a multifaceted risk profile. Firstly, it compromises the integrity of the safety mechanisms designed to protect against electrical shock. In a properly grounded system, a fault current, such as one caused by a damaged wire contacting a metal enclosure, will travel through the grounding conductor back to the source. This surge of current triggers the overcurrent protection device, like a circuit breaker, to trip, cutting off the part of the circuit and preventing potential harm to individuals who might come into contact with the faulty equipment. Without the grounding conductor, this fault current may seek alternative, unintended paths to ground, such as through a person touching the energized enclosure, leading to severe electrical shock or even electrocution. Secondly, the lack of a grounding conductor increases the risk of fire. When a fault occurs in an ungrounded system, the fault current may be limited, preventing the immediate activation of overcurrent protection. This sustained but lower level current can generate heat, potentially igniting nearby combustible materials and causing a fire. In contrast, a properly grounded system ensures that fault currents are high enough to trip the overcurrent protection devices quickly, minimizing the risk of fire. Thirdly, the absence of a grounding conductor can lead to damage to electrical equipment. Fault currents, if not promptly interrupted, can subject electrical components to excessive stress and heat, leading to premature failure. This can result in costly repairs or replacements, as well as disruptions in service. Moreover, sensitive electronic equipment is particularly vulnerable to damage from voltage surges and transients that can occur in ungrounded systems. Fourthly, failing to adhere to the NEC requirements for grounding can have legal and financial ramifications. Electrical inspections are designed to ensure compliance with the NEC and other relevant safety standards. An installation lacking a grounding conductor will undoubtedly fail inspection, potentially leading to fines, project delays, and the need for costly rework. Furthermore, in the event of an electrical accident or fire caused by the absence of a grounding conductor, the responsible party may face legal liability for damages, injuries, or loss of life. Therefore, ensuring the presence and proper installation of a grounding conductor is not merely a matter of adhering to code requirements, but a critical measure for protecting human life, preventing property damage, and mitigating legal and financial risks. When addressing the absence of a grounding conductor in an existing electrical system, it is essential to follow a systematic approach. Firstly, a thorough inspection should be conducted to verify the absence of the grounding conductor and to identify any other potential safety hazards. This inspection should be performed by a qualified electrician with expertise in grounding and bonding techniques. Secondly, a plan should be developed to install the missing grounding conductor in accordance with the NEC. This plan should include the selection of the appropriate size and type of grounding conductor, as well as the proper methods for connecting it to the grounding electrode system and the electrical equipment. Thirdly, the installation should be performed carefully and meticulously, following all applicable safety precautions. This includes energizing the circuit before working on it, using appropriate personal protective equipment, and verifying the integrity of all connections. Fourthly, after the installation is complete, The system should be tested to ensure that the grounding conductor is functioning properly. This can be done using a ground impedance tester, which measures the resistance of the grounding path. A low resistance reading indicates that the grounding conductor is effectively providing a path for fault currents to return to the source. Finally, documentation should be maintained to record the installation of the grounding conductor and the results of the testing. This documentation can be useful for future reference and for demonstrating compliance with code requirements. In addition to installing a grounding conductor, it is also important to ensure that all metal enclosures, raceways, and other conductive parts of the electrical system are properly bonded together. Bonding creates a low impedance path for fault currents to flow, helping to clear faults quickly and safely. Bonding can be accomplished by using bonding jumpers, bonding lock nuts, or other approved bonding methods. The NEC provides detailed requirements for bonding in Article 250. When selecting a grounding conductor, it is important to choose the correct size and type for the application. The size of the grounding conductor is determined by the size of the service entrance conductors, as specified in Table 250.102. Sheet 1. The type of grounding conductor can be either copper or aluminum, depending on the application and the specific requirements of the NEC. Copper is generally preferred for its superior conductivity and corrosion resistance, but aluminum can be used in certain applications provided that it is properly sized and installed. When connecting a grounding conductor to a grounding electrode, it is important to use approved methods, such as grounding clamps or exothermic welding. Grounding clamps should be made of a material that is compatible with the grounding conductor and the grounding electrode to prevent corrosion. Exothermic welding creates a permanent, low-resistance connection between the grounding conductor and the grounding electrode. In summary, the absence of a grounding conductor in an electrical service change is a serious violation of the NEC that can have significant safety consequences. It is essential to correct this issue as soon as possible by installing a grounding conductor and ensuring that all metal enclosures and raceways are properly bonded together. By following these steps, you can help to protect people and property from the hazards of electricity and ensure compliance with code requirements. Remember to always consult with a qualified electrician when performing electrical work and to follow all applicable safety precautions. The information provided here is for general guidance only and should not be considered a substitute for professional electrical advice.